Let's do next Newton's binomial theorem or formula. Newton's binomial formula. Let's let f of x be 1 plus x to the p power, where p here is any real number. And in fact, you might even wonder if it works if p is any complex number, though we won't get into it. We'd like to find an infinite series expansion for this. Though, if p is a positive integer, like 1 or 2 or 3 or 4 or 5, etc., the infinite series expansion will truncate and be a finite polynomial. It's not geometric, except if p happen to be -1. So we have to use the derivative. F prime of x will be, p is a constant, bring it down, p times 1 plus x to the p minus 1 power. Then with the chain rule, you get a derivative of 1 plus x to be 1. You'd multiply by a 1, which of course doesn't change anything, so I didn't have to write it. And from now on, with the other derivatives, I won't bother writing the times 1. Next, bring down p minus 1. Subtract 1 from the exponent. Next, bring down the p minus 2. Subtract 1 from the exponent. Next, bring down the p minus 3. Gets to be a lot to write, but hang with me here. Subtract 1 from the exponent, etc. What is the pattern? What would the nth derivative of f at x be? Notice that in each case, like consider the fourth derivative, in front of the 1 plus x to a certain power, you've got a certain product, p times p minus 1 times p minus 2, etc., where you've got 4 factors, in this case, matching the fact that we're doing the fourth derivative. So if we trust that pattern, and I see no reason not to, with the nth derivative, we'd have to have n factors. Since the first factor is really a p minus 0, the last factor is really p minus, in parentheses, n minus 1. That's going to be n factors. And what you subtract from p up here is going to be n, if you look at the pattern. And we could keep going. That's the general nth derivative. If p, again, is a positive integer, like 3, for example, once we get to that derivative, we'll get a bunch of zeros. We'll get, because p minus 3 will be 3 minus 3, and it'll give us 0. And everything after that point will be zeros, because they'll all have factors of p minus 3. And by the way, p minus, in parentheses, n minus 1, you could distribute the minus sign through and write it as p minus n plus 1, if you want. Now plug in 0. F of 0 is 1 to the p power, which is 1. F prime of 0 is p times 1 to the p minus 1 power, which is p. F double prime of 0, this is a single prime here, this is a double prime. Plug in 0 there, you get p times p minus 1 times 1 to the p minus 2, which is p times p minus 1. F triple prime of 0 will be p times p minus 1 times p minus 2. F quadruple prime of 0 will be p times p minus 1 times p minus 2 times p minus 3, etc. The nth derivative of f evaluated at 0 will be p times p minus 1 times p minus 2, etc. The last factor being p minus n plus 1. But I could keep going. Question? Yes, there is. These are related to factorials. That was the question, is this related to factorials? And yes, it is. Though I'm not going to get into the details because we need to do some more examples, but you might want to think about that. Yes, you can. You can relate it to something called, at least when p is a positive integer, at least you can relate it to something called a combination n choose r, for example. You have to generalize that in the case where p is not a positive integer, but yes, you can. Let's use these now. What do I have to do? I'm trying to find the Taylor series for this centered at 0 is my goal. I have to divide that by 0 factorial, but 0 factorial is 1, so it doesn't change it. I divide that by 1 factorial, which is also 1, so it doesn't change it. Then multiply by x. I have to divide this by 2 factorial, which does change it, so leave the 2 factorial in there, times x squared. Divide that by 3 factorial, divide that by 4 factorial, etc. Divide this by n factorial. By the way, this is a 3. Sorry, I made my 3 poorly. That's what I'll write down now. Let me call it, instead of saying it equals f of x straight away, let me call it p sub infinity, like an infinite degree polynomial. 1 plus p times x, right? P times x, p divided by 1 factorial, plus the next one was p times p minus 1 over 2 factorial times x squared. Then p times p minus 1 times p minus 2 over 3 factorial times x cubed, plus the next one would be p times p minus 1 times p minus 2 times p minus 3 over 4 factorial times x to the 4th, etc. For what values of x does this converge? Again, if p is a positive integer, like 1 or 2 or 3 or 4 or 5, we eventually get to the point where all the terms are 0. And it really doesn't have to be thought of as an infinite series in that case. It reduces to a polynomial. If p is a positive integer, in other words, 1, 2, 3, 4, 5, etc., the infinite series is said to truncate. It truncates and becomes finite. A finite polynomial, in fact, of degree equal to whatever p is, in fact, to a polynomial of degree p. And as a polynomial, there's no issues with convergence. Definitely is a well-defined thing that can be computed. I will go ahead and say which converges for all x. I'll put converges in quotes. There really is no issue at all with convergence for all x. If p is not a positive integer, whether it be a fraction, like a half, which would mean if p was a half, by the way, that I'd be taking really a square root, or a third, meaning I'm taking a cube root, or a fourth, meaning I'm taking a fourth root. We actually already did that example where p was 1/4. Or maybe even a fraction like 5/3, which would mean I'm taking a cube root and then raising to the 5th power. Or a negative fraction like negative 5/3, which means I'm taking a reciprocal before I'm doing the power. Or even an irrational number like pi. This converges for the absolute value of x being less than 1, just like with geometric series. So x is between -1 and +1. And the radius of convergence is 1. Series centered at 0. Radius of convergence is 1. Do not include the endpoints. By the way, if you do allow yourself to plug in complex numbers here, which you can, this interval of convergence along the real axis, the real line, will generalize to what's called a disk of convergence in the complex plane, where this is a real axis and there's an imaginary axis going up and down. But I could draw it and it would be there. You'd see it. It'd be just as real numbers. It becomes a disk of convergence, the inside of a circle, and the radius is truly a radius of a circle in that case. Actually, the imaginary axis would go through the origin, so it'd be like this. Let's apply this. Well, let's say let f of x be 1 plus x to the negative 4/3 power, which of course is the same as 1 over 1 plus x to the positive 4/3 power, which if you like is the same as 1 over the cube root of 1 plus x raised to the 4th power. Lots of different ways to think about it. But if we're going to use the formula that's up here, we need to figure out what p is. You got to write it in that form to figure out p. P is negative 4/3. That's the p. So now, use this formula with p equal to negative 4/3. So it starts off with the 1. Then it's p times x plus p times x. P is negative 4/3, so that becomes minus 4/3 x. Then it's plus p times p minus 1 over 2 factorial times x squared. P, negative 4/3, times p minus 1 is negative 7/3 over 2 factorial times x squared. So negative 4/3 and a negative 7/3 if it's not quite big enough for you to see there. Plus, next term is p times p minus 1 times p minus 2 over 3 factorial times x cubed. P is negative 4/3. P minus 1 is negative 7/3. P minus 2 is negative 10/3 over 3 factorial x cubed. I think I'll stop there, put the plus dot dot dots. Don't forget the plus dot dot dots. We do want these to be equal. I wrote p infinity up here, but it will equal the original function when x is between negative 1 and 1. This does actually equal f of x. That takes proof. We're not proving that, but it can be done. By the way, the radius and interval of convergence can also be figured out with the ratio test, but I'm not doing it. It's only a geometric series when p is negative 1. Otherwise, it's not geometric. Simplify. 1 minus 4/3 x. Do some arithmetic in my head here. This becomes positive 28 over 9, all divided by 2. Positive 14 over 9. X squared. This one I've got 3 minus signs, making a minus. 4 times 7 times 10, 280. I've really got 4 factors of 3 of them here, and then 1 from the 3 factorial. 3 to the 4th is 81. 3 factorial also involves a 2. 280 divided by 2 is 140. And then I only have the 3 to the 4th power left. So it looks like it's going to be 81. Minus 140 over 81, x cubed, etc. Check it after class if I went too fast for you there. It is a good thing to spend some time shortly after class checking your notes. At least, if nothing else, check the calculations. Check it with series. capital S series, plug in the function, comma, curly brace x, comma, then 0 is where we're centering it, and then comma, and then you want the highest power of x that you want to see, 3. There we have it, it checks. If you're interested in higher powers, then do that. Remember the point. The point is this is supposed to approximate this function. That might not seem like such a big deal since we have all this great technology. Why would I care about approximating the function 1 plus x to the negative 4/3 power? Come on, let me copy and paste. The two graphs are very close together when x is close to 0. This is a truncated version, a Taylor polynomial, so they don't equal each other exactly. But they are very close together when x is close to 0. As I include more and more terms, the approximation gets better and better on a bigger and bigger interval, though in this case, the interval never goes past plus or minus 1. But why would we care? Historically, people like Newton cared, and even after Newton through the early 1900s, because they didn't have computers or calculators that could do things like this. They needed ways to compute functions like this, also including e to the x, sine of x, and cosine of x, without technology. To do their science and engineering, they had to do that. So Newton, who was the first person to really exploit this to, for example, approximate pi and then uses approximations of pi for various things, led to other people doing this, led to people who made their lives as, well, you might call them arithmeticians or maybe early computers as people. Like in the movie Hidden Figures, they were called computers. They were working on doing calculations by hand before they had the technology. They had to use these things. In fact, they would often make their living by making huge, thick tables of function values that would cost maybe hundreds of dollars. They'd spend all their time doing arithmetic with these series to approximate functions. It's not the entire story. Taylor series is part of the story for approximating functions. The other part of the story is called interpolation. I've hinted at that already. If you take a class called numerical analysis, we do talk about interpolation in there. That's the other part of the story. I guess I should say there's even more. There's also properties of functions like trig functions being periodic. That helps too. Logarithms, properties of exponents, those kinds of things come into play as well to help make your calculation more efficient. So what about today with the technology? Well, we can still appreciate the old applications, but these do have what you might call higher level applications now. You still need to know this stuff to do more deeper analysis of differential equations, for example, or an engineering analysis of vibrations, vibrational modes, for example. Other kinds of infinite series are called Fourier series. We'll talk about that after the test a little bit. Come up in signal processing. Series are useful both theoretically and to get you any level of approximation that you might need. And yes, let me just emphasize once more. These are actually equal. You could call this P infinity. But it does equal the original function as long as the absolute value of x is less than 1. Okay. Next example. Our old friend. Favorite example, it seems, 3 over 4 plus 5x. I'm about to use the same formula I just showed you. This one for 1 plus x to the p for this example. How in the world? How are these related? You can do some algebra like the tricky algebra we did last week to see that they actually are related. This is the sum of a geometric series, as we saw last week. And I start with the same trick as before. Factor out the 4 out of the bottom. And so I don't have to use Newton's binomial formula. I could use the fact that this is going to be the sum of a geometric series, but I want to show you that you get the same answer with Newton's binomial formula. This time, put the 3/4 out in front and write this division by 1 plus 5/4 x as 1 plus 5/4 x to the -1 power. It's now looking closer to that. Except we have a 3/4 out in front. Well, that's no problem. Just leave it there. Leave it out in front. Got a 1 plus. Well, we don't have an x there. But that's okay. Just use this formula replacing x with 5/4 x. That's all you have to do. X here in this equaling that is an arbitrary number between -1 and 1. Just a symbol representing such an arbitrary number. You can think of 5/4 x as representing an arbitrary number between -1 and 1. I can use the same formula. What's p? It's -1. There we go. Use the formula. Leave the 3/4 out there. Then use parentheses. Look at this. 1 plus p times x. P is -1. So that becomes -1 times x. Oh, sorry. Mistake. 5/4 x. 5/4 x is playing the role of x. It's okay. You can do that. It's just called substitution. Plus p times p minus 1 over 2 factorial. P is -1, so this becomes plus -1 times -2 over 2 factorial times the thing playing the role of x, which is 5/4 x, quantity squared. I'm looking at that term right there. Now go to the next one. P times p minus 1 times p minus 2 over 3 factorial times the thing playing the role of x, quantity cubed, etc. Now distribute the 3/4 back through and simplify. 3/4 times 1 is 3/4. 3/4 times -5/4 x is -15/16 x. This should feel familiar. We did this exact example before last week as a geometric series. Next term, -1 times -2 is +2. Divided by 2 factorial is also +2. Becomes a 1. 5/4 squared becomes 25/16 times 3/4 becomes 75/64, right? X squared. For some reason, that's feeling not familiar. Did I make a mistake or is that okay? I guess it's okay. For some reason, that's feeling not familiar. Next term, I got 3 minus signs makes a minus. This is really a -3 factorial up top divided by +3 factorial. This becomes a -1. So we get a minus sign. 5/4 cubed is 125 over 64 times 3/4 is 375 over 256, 64 times 4, x cubed, etc. series 3 over 4 plus 5x centered at 0. I want to see out through the third powered term. Okay, looks good. What values of x does it converge for? This converged when p is not a positive integer, when the absolute value of x is less than 1, where x is that thing, that is, it's 1 plus x. Again, it's the 5/4 x that's playing the role of x. It's representing an arbitrary number between -1 and 1. This is going to work, converges, if the absolute value of 5/4 x is less than 1, which is equivalent to saying the absolute value of x itself is less than 4/5. We did this before. Our old friend 0.8. The radius of convergence is 4/5. The interval of convergence goes from -4/5 to +4/5, not including the endpoints. So sometimes you got to use a little trickery.